Hi, good evening. This is Sunday evening, and this week we're going to review what we did this previous week when we were talking about modular arithmetic, and I'm also going to give you a little preview of what we're going to do this coming week. So with modular arithmetic, what we've got here is, you can think of this as changing our numbering system, our counting system. Currently, we have a counting system that stretches from negative infinity, and it goes through 0, and then it goes up through positive infinity. And for our purposes now, we're just talking about integers. But in modular arithmetic, we restrict the numbering so that we're only talking about, first of all, just positive numbers, and also it's 0 through some highest number. And remember, modular or modulus kind of means remainder. So when we say something like mod 12, we mean a numbering system in which the only numbers that exist are 0 through 11, 11 being the highest possible remainder that we could have if we did a remainder after dividing by 12, excuse me. And if we did mod 100, that means only numbers 0 through 99 are allowed in our system. So the other thing about our numbering system is that rather than it being a linear stretch that goes from negative infinity up to positive infinity, this one is in the shape of a kind of a clock or a ring. In fact, these are sometimes called ring numbers because of this shape. So let's just do let's say mod 9. Okay, so we start at 0 at the top of our clock, and we go 1, 2, 3, 4, 5, 6, 7, and 8. And that's our entire numbering system. Okay, so it starts at 0, and it goes around to 8. And actually, it can go around and around and around again. All right, so the first thing we need to do is talk about where on the position we are when we talk about particular numbers. So if we do, let's do it this way. So if we do something like 12 mod 9, and sometimes we write the mod 9 in parentheses to say what we're doing is we're taking the number 12 and we're converting it into this new modular system in which the numbers only go from 0 through 8. So 12 mod 9 is, we start at 0 here and we just count it by 12. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we end up at 3 on the circle. So it's equal to 3 mod 9. And let's do another one. Let's say, how about 20 mod 9. So again, we start at the 0, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Is that right? I think I miscounted there. Let's try that again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, I'm supposed to end on 20. There we go. That's what I'm thinking about. So we end up on 2 mod 9. And what about, let's say, how about 21 mod 9? Well, we know that 20 mod 9 is 2, so 21 mod 9 must be 3. Okay, so those are some positive numbers. What about negative numbers? Let's say, negative 4. So we start at 0 and we count backwards. 1, 2, 3, 4. Negative 4 must be the same thing as 5. Oh, I'm mixing myself up. Negative 4 mod 9 is equal to 5 mod 9. Okay, so it's pretty easy to convert from our arbitrarily large set of numbers down to mod 9 in this case by just dividing by 9 and finding what the remainder is. And if you have to go negative, you just go backwards around the wheel. So it doesn't matter how many times you go around the wheel, you'll eventually end up somewhere, and that becomes your number. So one thing to notice here is that 21 mod 9 and 12 mod 9 both become 3. So we can say that 12, excuse me, that's going to go over me. So we'll do it over here. 12 mod 9 is equal to 3 mod 9, which is equal to 21 mod 9. And there's a whole bunch of other numbers that are all equivalent to each other. So these are called congruent values. So the value of 12 mod 9 is congruent to 3 mod 9, which is congruent to 21. And I think, let's see, if we go 1, 2, 3, 4, 5, 6, negative 6 mod 9. That's another congruent number. So we could go backwards around the wheel, we could go forwards around the wheel, and we'd all end up in the same place at that 3 spot. And that would be congruent values. Okay, so that's the idea of modular counting systems. The numbers only go from 0 up to 1 less than the modulus amount. So for mod 9 to go through 0 through 8. Okay, let's talk about how to do arithmetic. In particular, let's do addition. Okay, so if we have something like, let's do 6 plus 8 mod 9. Let's put our wheel back on the screen. Let's go 0, 1, 2, 3, 4, 5, 6, 7, and 8. So to do 6 plus 8, we start at 6, and then we add 8 to it by going in the same direction. 1, 2, 3, 4, 5, 6, 7, 8, and we end up at 5. So we know that 6 plus 8 is equal to 5. All right, so to add positive numbers, you just go clockwise around the wheel. And if you want to do subtraction, you just go counterclockwise. And where you end up is the answer. But if you want to do larger numbers, let's say we want to do 100 plus 236 mod 9. Okay, so we could go around and around and around and find our way to 100, and then we could add 236 to that by going around and around some more. But it so happens that there's a kind of an easier way to do addition when you're talking about modular arithmetic, and that is to take the first value and find its value mod 9 and add that to 236 mod 9. So in other words, we could actually do 100 mod 9, add that to 236 mod 9, and then the whole thing in the mod 9 counting system, and that becomes our equivalent value. So let's figure out what 100 mod 9 is. Now, I don't have a calculator handy, so I'm going to use, let's see, I think I need this one here. Whoops. Let me click on this. Here we go. So I'm going to use a programming language called Python. I'm just basically going to use it as a fancy calculator. So 100, and the percent sign is the symbol for modulus. So we get 1. So 100 mod 9 is 1, and 236 mod 9 is 2. Okay, so we know that this number here is 1, and this number is 2. So we end up with a total of 3 mod 9. So we didn't have to actually add 100 to 236 and then find mod 9. All we had to do is keep the number small by immediately hacking down the 100 to 1, the 236 to 2, and then just adding them together. Now, if the sum came out to be bigger than 8, then we would just do one additional step to bring it, again, the answer down into the right range. So for example, if this ended up being, let's say, 6, and this one ended up being 8, then we would get a total of 14, and then we'd have to do one additional mod 9 to get it down to its actual value of 5. Okay? So it so happens that for addition, instead of adding together two large numbers, you can just take the modulo of each one of the numbers individually, and then sum those together, and then take the modulo of that to get the final answer. So that's addition. And so it saves you a lot of going around and around and around the circle. Okay, how about multiplication? So again, if we have something like 6 times 8 mod 9, and I'll put the circle back on the screen, 0, 1, 2, 3, 4, 5, 6, 7, 8. Then 6 times 8 is the same thing as adding 6 over and over and over again. So we would go to our 6, and then we would add 6 again, and then add 6 again, and add 6 again, and add 6 again. We do that 8 times, and we finally end up at the right answer. The other way to do it, of course, is let's just multiply 6 times 8, and so that's what, 48, is that right? Let me just double check that. Yeah, 48. Mod 9. So we go 48 mod 9, and we end up with 3. Okay, so 6 times 8 in modular 9 is actually 3. But what if we want to multiply much larger numbers together? Let's say we did 100 times 236. Actually, let's pick some different numbers. How about instead of 100, we do something like 107? Okay, 107 times, whoops, let me bring that back on the screen here. 107 times 236. So just like with addition, we can find the modulo of each one of the numbers individually, and then do mod 9 of the whole thing at the end. So 107, let me type that into my calculator here. Mod 9 is 8. So 107 mod 9 is 8. And 236 mod 9, we know that's already 2. So you multiply those together and you get 16 mod 9, which is, and I just want to make sure I don't make a mistake, so that's 7. Okay, so the whole thing comes out to be 7. And we can verify that. If we switch over here and we do 107 times 236, is that big number? 25, 2 modulo 9, and we get 7. So we know that this way of doing multiplication works just fine. Actually, I don't need that icon there for now. Okay, so multiplication is easy to do. You can take your large numbers, do the modulo of each piece individually, and then do a modulo of the product at the very end. The nice thing about this is that if you have to deal with really large numbers, which is critical to things like cryptography in current computer systems, since we're using modern computers, which are maybe only 32 bits or 64 bits, you want to be able to take really large numbers, which might be 1,000 bits or 2,000 bits long, and cut them down to size so that you can do these operations quickly on a computer that has much fewer bits in its internal CPU. Okay, what about exponent? Okay, so if I do something like 6 to the 8th power. Okay, first of all, let's try that out so we know what the answer is. So 6 to the 8th power is a big number. 167, 9616 modulo 9. Oh, it comes out to be 0. So it so happens that that number is a multiple of 9. That'll work for an example, but I think a better example, let's change our numbers a bit. Let's do 7 to the 8th. Let's try it out. 7 to the 8th power. Four. Okay, that's come out better. So this is equal to 4 mod 9. So we know that's the answer. So that was done by taking 7 and raising it to the 8th power. So it's multiplying by 7 over and over and over again. Remember, multiplying by 7 is really just adding 7 over and over again. So we're basically going, we're starting at 7 and we're going zip, 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 zip around that wheel many, 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 many times. 167, 9616. So it's like like thousands of times around that circle and finally ending up at 4. Okay. But what if we have larger numbers? What if we did, well, let's do 107 to the 236th mod 9. Okay, so what is that? Let's find out. 107 to the 236th power. Okay, that's a big number. But 107 to the 236 mod 9 comes out to be 1. So the answer is just 1. Okay, so this big number is just 1 more than a multiple of 9, turns out. So so happens that you can't just take the modulo of this number and the modulo of this number and it'll work. In fact, let's try it and just see. It's not supposed to work, but let's try it. Let's go 107 modulo 9 and raise that to 286 mod 9 and then do mod 9 on the whole thing. Oh, we get 1. Not supposed to get 1. Well, actually, there's a 1 in 9 chance you'll get 1. This is what happens when you make up these numbers off the top of your head live. This sort of things happens. Let's try different numbers. Let's try 106. That comes out to be 4. Okay, 106 to 236 mod 9 also comes out to be 4. How about that one? That's 2. mod 9. All mod 9. This better not work. Okay. Whew. All right. There's an example of it not being equivalent. So right here, oh my gosh, I see I made a fatal error. Comes out the same. I think this is because we're using modulo 9. I apologize for this. It's all coming out the same. Well, we just keep trying stuff, right? 99. No, that's not a good one. 98 to 236 mod 9 is 1 again. 0. I think. Wait a minute. Hold on. It's 230. No. Let's just try 200. 1, of course. All right. Let's try a different modulus. Let's do like modulo 7. Let's go 100 to the 200th. Mod 7. All right, that's 4. 100. I'm boring all of you, but we'll see how this goes. 200 mod 7. mod 7 at the end. 2. Okay, I think I got that one right. 100 to the 200th power modulo 7. So we calculate the exponent first, or we do the exponent first, and we get 4 right here. But then if we do the base modulo 7 and we raise it to the exponent modulo 7 and then do mod 7 at the very end, we get a different answer. Okay, so that shows you that we cannot just simply take the modulo of both of these like we did for addition and multiplication and have it work. But what we can do, turns out, is that we can take the base, the 107. Actually, what was the example we just did? Let's scratch this out. That one doesn't work. Or it's not a good example. Let's do 100 to the 200th power mod 7. Okay, we know that's going to be 4. Because we nope, we know it's going to be, we know it's going to be 4 because that's what we calculated. There we go. So it turns out that actually you can do the 100. So you can go 100 mod 7, raise that to the 200th power, and then do that mod 7, and you'll still get 4. Okay, let's try that out. (100 mod 7), raise that to the 200th power, and then we'll go mod 7, and we get 4, which is the answer we're looking for. Let's try it the other way. Let's do 100 to the 200 mod 7, and then all that mod 7. And that doesn't work either. Okay, so what I just showed here is that you can't do a modulo on the exponent, but you can do it on the base, and it'll be fine. Okay, so this technique works, but you can't individually modulo each of the pieces. Now, if you're like a programming language other than Python or one of the other several programming languages that handle arbitrarily large numbers fine, or handle it well, then you've got a problem, which is how do I still keep the numbers relatively small? And there's an algorithm that the computers use to do modular exponentiation. So let me show that to you. It's going to take me a while to bring up that image. Okay. So here's the algorithm. So this is modular power. It takes in the base, the exponent, and the modulus. And then it works like this. First of all, it tentatively, or it initializes the result to 1. So we start out with a result of 1. And then the first thing we do is we take that base and we knock it down by doing the modulo on it, which is what I showed you on the previous page. So we can take that base of 100 and we can do modulo 7 immediately. And so we're only working with a number that's at most 6 in this case. So that's what this next line does. And now we're going to run a loop. We're going to be running the loop as long as the exponent is greater than 0. So what's going to happen as the loop is running is it's going to take the exponent, which started out at what, 200, and it's going to start decreasing it until it gets down to 0. So this loop is done when we finally run out of exponent to work with. And then this next line says if the exponent is odd. In other words, if we divide by 2 and we get a remainder of 1, then we want to do this thing here. But actually, let me draw a little line here. When exponent is odd. Okay, so that's one way of thinking about it. But another way to think about it is in terms of binary. When a number is odd, it means that there's a 1 sitting over in the ones column. In other words, if I have a number like 101100, okay, we can tell immediately that this number is even because there's a 0 sitting here. But if we have a number like 101101, we know that this number is odd because there's a 1 sitting here. Okay, so what this algorithm is going to do is it's going to basically take the number and treat it like it's a binary number. And you can see there's a line here which is to take the exponent and divide it by 2. This is integer divided by 2. So you don't end up with a decimal number here. You end up with just an integer number. And what that has the effect of is basically lopping off the rightmost digit. So when you divide a number by 2, you just take the rightmost digit and you just get rid of it. It's the same thing as dividing by 10 in base 10. If you take a number like 236 and you divide it by 10 integer-wise, you just lop off the 6 and you end up with 23. Right? So 236 divided by 10 is equal to 23. You just took the 6 and you got rid of it. So when you take a number and you divide it by 2, you're taking the rightmost binary digit and you're just lopping it off. Okay, so that's what the loop is doing. It's essentially working its way through the binary number from right to left. And anytime there's a 1 sitting in the rightmost column, it's going to do this thing in the middle. So this thing in the middle is to take the result, multiply it by the base, do modulo n again to knock it down to size, and then store that back in the result. Then regardless of whether there was a 1 there in the rightmost column, it's going to take the base and square it, and then do modulo n. And then as we described before, it's going to take the exponent and divide it by 2. All right, so let's try it with some numbers. Let's do like 11 to the 23rd mod 7. Okay, so as we're doing this loop, what we should do is keep track of these variables as they're changing. So we've got result, which is changing. We have base is changing, and exponent is changing. And they start out being 1, which comes from this line right here. Base immediately gets knocked down. So from 11 down to 4, because 11 mod 7 is 4. And exponent starts out being 23. Okay, so this first line here, 1, 4, 23, is the initial line, and we're now ready to begin the loop. Okay, so the loop is greater than, the exponent is greater than 0, and it's odd, or in other words, there's a 1 sitting in that ones column. So we're going to take result, multiply it by the base, and then do modulo 7. Okay, so result is 1. We're going to multiply it by the base, which is 4. So 1 times 4 is 4. And then we do modulo 7, and we still get 4. So result is now going to be 4. And then we take base and square it. So we get 16. And then we do modulo 7 on that, and we end up with 2. And then we divide the exponent by 2. So we just basically lop off the right-hand bit. So 23 divided by 2, I think, comes out to be 11, if I'm not mistaken. And let me just verify that here. 23 divided by 2, yep, comes out to be 11. Okay, so then we come back up here, and the exponent is still greater than 0. And the exponent is odd, so result equals result times base. 4 times 2 is 8. Then we do modulo 7, and we get 1. So it's back to 1 again. And then base gets squared. 2 times 2 is 4. Modulo 7 is 4. And then exponent gets divided by 2 again, and we end up with 5 there. All right, repeat. Exponent is greater than 0. Exponent is odd. So result equals result times base. 1 times 4 is 4. Modulo 7 is 4. So actually the result is flip-flopping between 1 and 4. And then base gets squared. 16 mod 7 is 2. And exponent gets divided again. And so we end up with 2 there. Okay, we're almost done. So we come back up here. Exponent is greater than 0. It's even this time, so we're not going to do this piece. We're going to go straight into squaring the base. 4. We're not going to touch the result, so that stays 4. And then the exponent gets divided, and that's 1. And I'm sorry, it's gonna cover me up a little bit. So I think what I'll do is I'll see if I can erase me for a moment. There we go. And finally, we come back up here. Exponent is still greater than 0. It's odd. So we're going to go result equals result times base mod n, in this case 7. So 4 times 4 is 16. Mod 7 is 2. Then we're going to square the base. 16 mod 7 is also 2. And exponent goes down to 0. And at this point, we're done. So this 2 should be, this should be the answer. And let's see if we're right. So here I am again. So I'm going to try it over here. 11 to the 23rd mod 7 is 2. Okay? And by the way, 11 to the 23rd is a big number. So you can see how that huge number there can't be held in 32 bits or 64 bits of a computer. Maybe it can be held in 64, but I doubt it. Can't be held in 32 bits on a computer. So we need an algorithm like this one over there. An algorithm like that one to be able to do this. Notice that none of the numbers here, anywhere in this table here, got very big. Okay, so this is an important algorithm for computers to be able to do exponents, but in a modular counting system. So basically, none of the numbers get bigger than n, whatever that happens to be. All right, so that's exponent in modular arithmetic. All right, so at this point, I want to see if there's any questions. I've got a few people watching, but nothing going on in chat. So if you have any questions, feel free to post them anytime, and I'll try to answer them. I don't see anything right now. So let's do something called modular identity. Okay, so this is actually a little preview of something coming up in the week ahead. So identity under addition, so actually let me erase this. Let's call this additive let me spell this right. Under regular numbers, says this. If I have a number a, let's say for all a, there exists a b such that a plus b is equal to 0. Okay, that's what additive identity says. That for any number a, actually we say any integer, we'll say integers. For any integer a, well actually these are regular numbers, so it doesn't matter whether integers or reals, but for any number a, there exists some b such that if you add the two of them together, you'll end up with 0. Okay, let's try it out. So let's choose a is equal to 5. So for what value of b is there so that when you add it to a, you'll end up with 0? Well, obviously the answer is like -5. And we choose a equals 100, then b is equal to -100. Okay, so one way to put it is that b is equal to -a. That's pretty easy. What about, so let's switch to a new screen. What about additive identity under, let's say, mod 7? Could be mod anything. Well, let's do mod n. Okay, so it's the same sort of thing. Whoops. For all a, there exists a b such that a plus b is equal to 0 mod n. So there's really only one change, and that's that one up there that says mod n. So let's do an example. Let's say a is equal to 5. What does b equal? Well, so you might say negative 5, obviously. If I take 5 and I add it to negative 5, I'm going to get 0. But let's talk about just numbers within 0 to n minus 1. Right? So let's talk about, let's say, mod 7. So let's set n is equal to 7. So something added to 5 equals 0 mod 7. So one possible value for b, of course, is negative 5, but another possible value is 2, right? So if I take 5 and I add it to 2 and I do mod 7, right? 5 plus 2 mod 7 is certainly equal to 0. And there's many values of b that'll work. Another one might be 9, right? 5 plus 9 comes out to be 14, and then you do 14 mod 7 and you get 0. Okay, so there's many different values of b, which when added to a gets you 0. So that's the difference here in identity under modular arithmetic, is that there's many possible values of b, and you're going to keep everything constrained, ideally keep everything constrained within 0 through 9. So really, the interesting number is not this one, and it's not this one, it's the 2. Okay? So here, that's the critical thing here, is that the inverse, the additive inverse of 5 under mod 7 is not negative 5, it's 2. Okay, does that seem weird? 5 and 2 are inverses of each other because when you add them together, you get 0. And the reason why 2 is the interesting one is because it's the one that's between 0 and 6. 9 is out of range and negative 5 is out of range. Okay, so this is the interesting one. Okay, so 5 and 2 are additive inverses in mod 7. Does that make sense? Okay. So that's additive identity under modulo. Let's try, oh, what am I doing here? Click that, there, new screen, here we go. Multiplicative identity. And this is regular. So regular real numbers. For all a, there exists a b such that a times b, and you'd think the answer there would be 0, but it's not. It should actually be 1. And the reason why it shouldn't be 0 is because there's only one b that when you multiply by a gives you 0. But so under multiplication, the identity value that you're interested in is the 1. So we want two numbers which when multiplied together gets you 1. So let's try a is equal to 5. So what number when multiplied by 5 gets you 1? Well, that's easy. It's 1/5. Right? So 5 times 1/5 is equal to 1. And if a is equal to 100, then b is 1 over 100. Okay, seems obvious. So another way to put it is b is equal to 1 over a. Or another way to say it is a to the negative 1 power. Okay, that's the same thing. So a to the negative first power is the same thing as the reciprocal of a. And actually, this definition is really the interesting one. So b is equal to a to the negative 1 power. Okay, that's under regular arithmetic. But now, you can probably tell where this is going. Let's do multiplicative identity mod n. Oops, I lost my screen, so hold on just a second. I think I can fix this. Did we get it? Almost. Hold on. Got a little bit of work to do here. Sorry about that. It's a little bug in my program. Oh, I think that we almost had it. I'm sorry about this. Here we go. There we go. All right. We're back, mostly. All right, I apologize for that. Where were we? Oh, yeah. So for all a, there exists a b such that a times b is equal to 1 mod n. All right? So here's where things get a little strange. Let's go n equals 7. Let's do a equals 5. So what we're trying to do is find a value for b such that when we multiply them together, we get 1. So you're thinking, well, that's easy. You know, it's just 1/5. Okay, but we're just talking about integers here. So 1/5 is not an integer. Okay, this is not what we're looking for. We're looking for an integer. Then when multiplied by 5 gets you 1. So then you got to think about, okay, well, how are we going to do this? So let's try b is equal to 1. So that means 1 times 5 is 5. That's not it. How about b is equal to 2? 2 times 5 is 10. 10 mod 7 is 3. That's not it. How about 3? 3 times 5 is 15. 15 mod 7 is 1. Okay, so b is 3. So if a is 5, b is 3. 5 times 3 is 15. Modulo 7 is 1. Okay, so 5 and 3 are multiplicative inverses. That's the word here, is inverses, multiplicative inverses of each other. Let's just try the others. How about b is equal to 4? Okay, so 5 times 4 is 20. 20 mod 7 is like 6. That's not it. How about 5? 5 times 5 is 25. Modulo 7 is, does that work? 5, wait. 25 mod 7. No, it's 4. Never mind. And b is equal to 6. 6 times 5 is 30. That comes out to be 2. That's not it. So this is the answer. Okay, so it's still true that b is equal to not 1 over a, but a to the negative 1. Remember that definition I was talking about last time, the important one? But really what we're saying is, and this is kind of a nonsensical definition because, you know, what does this mean here? But what we're saying is that the multiplicative inverse of a is the number, so that when you multiply it by a, you get 1. That's what the multiplicative inverse is. And so for 5, it's 3 under modulo 7. Okay, we can try a different number. What if a is equal to 4? Okay, so what, when multiplied by 4, gives us 1? So it's not 1. 2, actually it's 2. Because when I multiply 4 times 2, I get 8. 8 modulo 7 is 1. What about if a is equal to 6? So 6 times 1, that's not it. 6 times 2 is 12, that's not it. 6 times 3 is 18, that's not it. 6 times 4 is 24, that's not it. 6 times 5 is 30, nope. 6 times 6 is 36, oh, there we go. So the inverse of 6 is also 6. 6 times 6 is 36, modulo 7 is 1, and that's what we're looking for. Okay, so we can actually build up a table. For every value of a, we're going to find a value of b that is its multiplicative inverse. So we're going to find a value that when we multiply it by the original number and we do modulo n, we get 1. And so if we build up that table, we get some interesting results. Yeah, let's do it like this. Let's go a and b. We go 1, 2, 3, 4, 5. Oops, sorry. This is going off the screen. So let me start over again. Let's do it up here. A and B. 1, 2, 3, 4, 5, and 6. And there's a reason why we don't put 0 there. Is because we can't find any number when we multiply by 0 it gives you 1. So for B, 1 times 1 is 1. 2, we know that is 4 from here. For 3, it's 5. We know that from this up here. For 4, we know it's 2. For 5, we know it's 3. And for 6, we know that it's 6. Okay? So the thing to notice here is that for every value of a, there's a unique value of b. There's a one-to-one mapping between a and b. And if that exists, if there's a one-to-one mapping between those two values, that forms something called a field. And this is going to be critical for things like cryptography, because when we're doing cryptography, if we want to encrypt something, we start at a value of a and we find its equivalent value in b, and then if we want to go back, we have to be able to get back to a again. If we look down the column of the b column here and we find there's some duplicate numbers, like let's say the number 4 appeared twice, then we wouldn't have a field, and that wouldn't be a good way to do encryption, because there would be like for every value of a, there's 2 values of b, which means that there's no unambiguous way to decrypt back to the original value of a. So you have a field if one-to-one mapping from a to b. So that's going to be an important thing. And so I think what I want to do is kind of leave it there. And like I said, this is sort of a preview, and this is going to become important and what in the weeks to come. And so what we're going to be doing over the next week is, well, to find the multiplicative inverse, let me back up. To find the additive inverse under modulo n, that's easy, right? You just do the negative number. And actually, let me switch screens here. This one here, this is the additive inverse. You can find the 2 fairly easily, actually, by starting at the -5 and do -5 mod 7, and you end up with 2. So that's really easy to calculate. Just negate the number, do modulo n, you'll end up with a positive number, and then you've got your additive inverse. Easy. But multiplicative inverse, note what we had to do here. We did kind of trial and error. We just looped from 1 up to n-1, and we tried them all until we found one that worked. Or we can build this table, and we can look to see what. But if we build a table, we still have to run this loop from 1 to 6. So what we need is a way to calculate the inverse, the multiplicative inverse, that doesn't involve essentially trial and error. Particularly if the numbers get big, like if n is 1,000 or more, And if a is also a big number, we can't be writing a big loop that goes from 1 to 1,000 in order to find the inverse. We got to find a faster way to do it. And that's what we're going to be doing up in the next week, is exploring some ways of finding this inverse without doing an exhaustive check of everything. Okay, so at that point, I think I'm going to leave things as they are. If there are any questions, go ahead and post them in the chat. I'll wait about a half minute or so, and if I see nothing, then I'll bid you all a goodbye, a good night and a goodbye, and I'll see you in class. Okay, I haven't seen anything in the chat, so have a good night, everyone, and I'll see you all later.